Welcome to this presentation on the Introduction to Exergy. If you want the handout that goes with this lecture, please check the notes in the video for a link to where you can pick those up at. I'm going to start off with a couple questions here. True or false? Is energy conserved in every device or process? Right, is energy conserved? Or energy is conserved? I guess I should have asked the question versus the statement. Yes, energy is conserved in every device or process. Energy cannot be destroyed, true or false? Right, hopefully if you've been through a thermodynamics class like ours, you know this is very much true. Energy cannot be destroyed. All energy is useful, true or false? All right, this one might give you a little bit of pause. And what we're going to see today is that this is false. Exergy helps us to see what energy we can use. So here's an example of that. So say we have a boundary here, initial system, with some fuel here in the middle, and it's burning off. We got this nice little flame here, and air has initial temperature here, and we just have this boundary of our system. And we see with time, right? So time goes here to the left from picture A, B, and then C over here. Time is progressing, and we also see that energy quantity is constant the whole way across. So here, while the fuel is being used up, we still have the flame, and this temperature is increasing. It's going up as we're heating up, as the fuel is being converted to thermal energy. And when we get over here to see, the fuel is all gone, flame is out, but the temperature has increased now some delta T. All right, so the energy is still there. We still have a constant energy. We've done everything, these other two true statements. All right, so we've maintained these two things. But we find it's not as useful anymore. We're not going to burn anything else. All right, so how do we quantify this? What does that look like? How do you define the usefulness of different types of energy? All right, you think about that for a little bit. How do you quantify the usefulness of different types of energy? How do you know when it's still valuable for you versus getting some energy from some process and saying, well, I can't really use that? All right, so let's look at that. That's going to be what this thing is we're calling exergy. All right, so look at some definitions here first. So exergy, and this is spelled correctly. It looks a whole lot like energy, and that's kind of on purpose. It was first termed by MIT in the 1940s as availability. They called it availability. But in Europe, the term exergy was coined in the 50s. And exergy stuck around probably because it rhymes with or sounds like energy and entropy, and it doesn't require, well, I guess it kind of does require an explanation as availability. But I think the cohesiveness with entropy and energy helped it to win out, as it were. But exergy is the maximum theoretical work. When you talk about that usefulness, we're talking about work here in this case. Maximum theoretical work attainable from an overall system consisting of a system and the environment as the system comes into equilibrium with the environment, as it passes to the dead state. All right. So in the previous slide, if we go back here, or a couple slides back, all right, we have this system here, well, the overall boundary system, and it's coming in equilibrium with the environment that exists here on the inside. So how does a system come into equilibrium with its environment? All right, so what is this dead state thing? All right, so dead state is when a system of interest is at the temperature and pressure and at rest relative to the environment. In some ways, you can think there's no delta anymore. There's no delta for the temperature, the pressure, and overall velocity or potential energy of the environment. And we're going to see that in the exergy equation. All right. So let's keep thinking about this kind of analogy-wise. How do you think you see exergy in your life? If we're talking about it's relative to a dead state, and that might bring some images to mind, how do you think exergy looks like in your life? How about we just look at a daily case? All right, so here's your day. I'm making maybe a huge assumption here that you're waking up at 7 a.m. But here's your day as it goes to noon. All right, 12 o'clock here all the way to maybe bed here. All right, and so we're looking at overall exergy, what you have here. So if we look first, and we're going to call that 0, so 0 exergy. And so here's the first case. So what do you think is happening here? All right, it increases initially here. Again, this is 7 a.m. And so say this is Tuesday, Thursday. For my students in my class, we have class at 8 o'clock. All right, so what do you think is happening here? All right, hopefully you see that you're getting up and moving around, and then you're sitting down for my class. All right, so we have potential and kinetic energy. So you're laying in bed, and your potential energy increases because a couple of things. Well, your potential energy increases maybe, let's say, to here, because you're standing up, hopefully. And then it gets up to here because you're moving around. So you have both potential energy here and some kinetic energy here. So what you see here is during class, unless we get up and move around, you're basically going to be sitting, and your potential energy is going to be remain constant. But it's higher than what you were at your dead state when you were sleeping. All right. You get up and move after class. You get up and go somewhere else. You sit down probably again. Maybe have a bathroom break. Sit down, get some more work done before you get up and go to get lunch. Right, and then you get up and do other things throughout your day. Back here, I'm thinking hopefully there's some exercise. Right, so extra amount of kinetic energy happening there before you go back and study and doing stuff before you go to bed. All right, so that's one piece of energy. Let's look at another piece of energy. All right, so wipe the stuff away, but we'll add in this one. What do you think is happening here? So again, it initially is low and then it increases. It may be not actually this low, it may be a little bit higher. But let's say this is your internal energy. All right, so up here that's happening, again, as you first wake up, you're getting some breakfast here. All right, so you've added energy to your body. And then maybe if you drink some water, you could say potentially some energy there. But otherwise, if you're not eating any other food, you'll see it. Your energy, the amount of energy you have within your body, is decreasing with time. Now, this is actual energy within your body as opposed to, let's say, energy that you feel. Like you feel energetic, that might change up and down. But actual internal energy of your body is what's seen here. So we see that go down at lunch. We eat some food. It goes back up. And then slowly goes down unless we have any snacks. Till dinner. Again, goes back up. And here I'm saying you probably have a nice little snack. And maybe not so healthy. So I'll put healthy question mark right here. And the reason why is because it drops off much more quickly. Say it's just a bunch of potato chips or something, and your body's going to burn that much more quickly, and it drops off much more rapidly. All right, but if we combine these two, we get the total exergy for the day. All right, so we get our orange line plot here. So basically I just added. All right, so you can see here. So if we take this point here on this line, so this height, and if I just add it to here, it should end up at that point right there. So adding those up, we get the orange plot there. All right, so total exergy, the useful energy that we have during the day, again, from food as well as just our body putting us up in the air, potential energy and kinetic energy as we're moving around. All right, you could extend this further and you could say, well, maybe we could go back and we could put actually when we die, we always have a little bit of exergy because we could keep going till we're dead. It's like, well, let's keep this alive and we'll go based on our environment of 0 being when we're asleep. But if we go even further, we can get maybe a little biblical, and we can say go down to ashes, dust to dust, from Genesis 3:19, and say that's the point when there is actually no useful energy left from us. But anyway, so there's a lot of potential ways that you could measure exergy against. So you'd have to kind of declare what your environment is. In some cases, it's more clear, but this analogy it might break down a little bit with time. All right, so exergy of a system, we've talked about and hinted at some of these things. So we have some internal energy. So we're looking at the internal energy of where we're at with our system versus, this is the environment's internal energy. All right, we're going to look at the pressure of the environment and then look at the velocity that our system is at relative to the environment. All right, so our environment could be moving or it could be stationary. So if it's stationary, it'd be 0, but if it's moving, it would be something greater than 0. Over this way. All Sorry about that. Temperature, we have some entropy too. We can look at that. So we multiply that through, and then also some kinetic and potential energy that could be increased as well. Again, so we don't work with total energy, internal energy much, right? We don't usually deal with this. So we're going to move down here to specific exergy, where it's on a per unit mass basis, and also do that calculation. So we get a specific exergy in the end, which is basically just our exergy per unit mass. All right, so let's look at applying this to just seeing how it worked with a vapor dome system. So here's our example. Again, you can see this on the handout, or you can just follow along on the slide here. We've got 3 different processes that are happening. So 1 to 2 is happening here, 3 going over to 4, and 5 going over to 6. Our dead state for all these is down here. All right, so we want to look at how do these processes compare to the dead state. Are we seeing exergy overall increasing, or is it decreasing? All right, so here's our plot again up top. All right, so if you look at the exergy equation, this is relative to the dead state. So that's this point here. And this point is going to be both. We're going to start with process 1 to 2. That is going to be 1, and it's going to be 2. So what I want to do for each one of these items here, so we're just going to look at these 3, not worry about kinetic and potential for now, because we're just looking at the states that exist. So if we look at the internal energy, we want to say, okay, how does the difference between state 1 compared to the dead state, and how does state 2 compare to the dead state, and which one's greater? Because that'll basically say which of these terms, and ultimately what exergy is greater between these two. So for the internal energy at 1, we'd expect that to be higher than the internal energy at 2. It's going to be greater than the internal energy at 2. So overall, this term for internal energy will be greater for 1 than 2. For the specific volume, again, 1 will be greater than 2, right, being up there at the higher pressure temperatures. How about entropy? You can see if this is a TS diagram, then 2 is definitely going to be greater than 1. So overall, what we find from process 1 to 2 is that exergy would decrease. All right. So it's a little bit of the back of the envelope. We maybe actually should look at the values, but overall, I want to give you an impression of what's going on here. So because 1's greater than 2 here, greater than 2 here, 2 is greater than 1 here, but the impact of that versus these two, exergy is still going to decrease as we go from 1 to 2. All right, so let's apply that same logic here to 3 to 4. So internal energy is going to be greater at 4. The specific volume is also going to be greater at 4. And the entropy is also going to be greater at 4. So that one's really easy. We can see that that's clearly exergy is going to be increasing as we go from 3 to 4. All right, so 5 to 6 do the same thing. So internal energy, 5 is greater than 6. And for a specific volume, we got 5 is greater than 6. And for entropy, we know that 5 is greater than 6 as well. So in this case, it's the opposite, so we have decrease in exergy there. All right, so hopefully that makes some sense. We look at the different values and where they would show up, at least in this case, with the vapor power systems. Again, probably want to look at values to be sure, but especially for process 3 to 4, 5 to 6, it's very clearly increasing from 3 to 4, decreasing from 5 to 6. All right, just to give you some more kind of ways to think about this, and maybe you've already seen this, hopefully, but just make sure everything's going that direction. We can think about total energy. Sorry, it's spiking there. We can think about total energy existing here. It's one big circle of energy. And exergy is some, hopefully, large piece of that pie. It's some part of the total energy that exists in this system. But there is some part here that's the unavailable energy that we cannot access. And exergy is really just highlighting the stuff that we can access. Right, so if we look at the equations we're familiar with energy, right? So we have the internal energy v squared over 2, and potential energy Gz. So for Exergy, we'd have, again, our internal energy, P times delta V, temperature and change in or comparison of the entropies, and kinetic and potential energy. All right, so that's for a fixed mass. If we go to an open system, right, we're going to have energy as a representation of the enthalpy, kinetic and potential energy. We all have enthalpy here as well. And so how did enthalpy show up here? We haven't looked at that, seen that in Exergy yet. Let me just go back a slide. Maybe you'll see it real quick. All right, so remember, enthalpy is a combination of internal energy plus PV. And so here's P and, or U, and there's PV. So if we combine those, we'd see these here in our Exergy equation. For a flowing system, all right, temperature times the delta entropy, and then kinetic and potential energy. All right, we can see how those compare. Let's see how this works with just energy transferring through a wall. What does it look like there? Again, if Exergy is some portion of the total energy that works. So we have some, we call it air over here maybe, some temperature that's higher than, let's say, the air outside, and it's got to go through a wall here, so we see some temperature distribution like that. For heat transfer, the overall heat transfer rate through that wall is going to be constant. It's going to be Q. All right. The entropy transfer says that if we look at Q over T, we have this some entropy generated. Right? We can't go through, well, we can possibly go through if it's reversible. Q over T1 would equal Q over T2, but in reality, there's going to be some entropy generated. For Exergy, right, we have this 1 minus T naught over T, so we're comparing against the environment, or the, sorry, excuse me, comparing against the dead state. But we're going to lose some available energy. All right, and what we're left with is the actual available energy that we have after we go through that wall. All right, so hopefully 3 representations that help you get a better sense of what this Exergy really is. All right, another piece here. You're just a vapor that appears for a little while and then vanishes away. You have some Exergy. You're given Exergy. God has given us Exergy. How are we going to use that? What does that show up? How do we move through life and apply that to what we can do? All right, so just a bit of vapor. All right, maybe saturated vapor to start out with. I'm not sure if you're as hot as 120 degrees C. If you are, I'm not sure how you're listening to this presentation right now. But if we take some vapor and going at 30 meters per second, be 6 meters high relative to the dead state here. All right, a lot of potential energy that just this piece of vapor, a little bit of vapor could do. But maybe the same question I can ask of you, being a lot more than just a piece of vapor. What is it you can do? What is kind of Exergy that you have, and how are you going to spend it? All right. A couple final things for some Exergy aspects I want to highlight here. Exergy is a measure of the departure of the state of a system from that of the environment. So hopefully we've seen that already. It's like, how far are we away from the environment? The value of Exergy cannot be negative. All right, so if you have questions about that, ask me. But what's really neat is even if you are below the dead state, so you can go below the dead state. So say the dead state is the environment in the room you're sitting in. You could be colder than the room. All right, and as you're cold or whatever is cold, say you have a soda or something that's colder than the room, you can derive Exergy, useful energy from that soda heating up to the environment. All right, so it still would not be negative in that case. So Exergy cannot be negative. Exergy is not conserved, like energy is, but is destroyed by irreversibilities. All right. Exergy can be regarded as the magnitude of the minimum theoretical work input required to bring the system from the dead state to the given state. So if we start at the dead state and work up, to our given state. That's another way we can think about how exergy can be found. What's the work that takes us to get us from dead state up to where the current or given state that we're looking at. Finally, when a system is at dead state, it is in thermal and mechanical equilibrium with the environment, and the value of exergy is 0 when we get to equilibrium. There's nothing else, and there's no other useful energy that we have that we can do. All right, so hopefully that gives you a good idea about what exergy is. In class, we'll get to an example, which you can see on the handout, and give you some exposure to doing that. All right, thank you for listening.